There we go. All right. So, afternoon, everybody. My name is Jeremiah Griffin. I'm a computer science and mathematics major here at CMC. I'm also the next Vice President of Leadership for Phi Theta Kappa Beta Rho here on campus. I've been full-time at CMC since fall of 2010. I'll be graduating next spring. This project that I'll be presenting has been in development since August of last year. And Professor Markin started actually getting on the project. The initial inception of this idea was to write a relatively simple simulator for strictly defined single body conservation of angular momentum problems. Our ideas since then have become far more ambitious. There's a lot of struggles in the way with it. The goal we have apparently settled upon is a full-featured modeling and simulation tool for designing and analyzing multi-body simulations of linear and angular motion as described by Newton's laws of motion and gravity. Today, however, I'll be presenting a model that coincides with our initial design that is just angular motion. Now, this project is a bit different from what the other students have just presented. It's not created using a third-party modeling tool. It's made using a simulator that I have personally written, which currently stands at about 6,400 lines of C++ code. It's important to understand that I'm not presenting this model. I'm presenting the entire program behind the model. The model, however, represents a star that's superficially similar to our sun. It's yellow, it's just as big, it's spinning at the same speed, but it's twice as massive. This star is about to undergo some pretty extensive changes as it collapses into a neutron star. The purpose of a simulation like this is to observe how the system changes under the conservation of angular momentum. Simply put, this body needs to spin faster to conserve its angular momentum as its radius collapses and its mass stays the same. So before I start the simulation, I want to point out where you should be looking. So naturally, you want to watch the visualization of the star. I have no doubt that everybody will be watching that. But you also need to pay attention to this graph down here at the bottom. This is going to be how the radius is changing as the simulation progresses. And people who are interested in the physical side of this simulation should be watching these values on the right. What you should observe is that the angular momentum, which is just angular MO on there, is going to stay the same, so is mass. Everything else is going to change. And you can verify that this simulation works through checking those values. So I'm going to start it, but for the sake of everybody's time, the simulation is going to go through at a rate of 1 day passing every second of real time, so that you don't have to wait for a month to watch it. So for the first 5 days, the star is rotating at its normal speed. And then after 5 days, it speeds up as it collapses. Now for the next 20 days, it maintains the same speed. It's not changing in mass anymore, radius anymore. But we can see that the radius is stabilized at about 12 kilometers. That diameter is about from here to Yucca Valley High School. And it used to be as big as our sun. So now that it's collapsed, it's rotating about 1,500 times every second in the simulation, which maps to 1.3 billion times every real second. But did anybody notice anything interesting or unusual as the star collapsed? Again. I'll get to that. What happened was the rate that it was speeding up increased as it got smaller. A new physics student studying the equations of angular motion would not realize this without seeing it, because it's not obvious just from the formula themselves. This is one of the reasons we wanted to simulate angular motion. It's an important topic that can be difficult for students new to the concept to visualize and fully understand. We would like to use this software in the physics labs here at CMC and at other colleges so that students can create their own models and experiment with motion laws to get a deeper understanding of how it works. So would anybody like to see it again, or any questions? Yeah. Yeah, I'm running out. now it's speeding up. See how it got a lot faster, how it's speeding up towards the end? That's one of the things that you wouldn't know just from looking at the map. You have to actually watch a simulation, which we currently don't have tools for at CMC. That's what I want to do with this. It's actually spinning a lot faster than that. It's just that the screen cannot project how quickly it's going. Your eyes actually really feel it. That's my presentation.
Thank you.